All right. There's a source that uh, undergoing radioactive decay, and what type of emission is it going, and radiation detector. Okay, the diagram shows a system used to control the thickness of aluminum foil being made in a factory. What is the most suitable ra radioactive source for this system? Okay. Now it's measuring the thickness, right? What it does is, let's say it identifies, like, you know, whatever, depending on the source, whatever it is, let's say 10 radiation. I'm so sorry for this. But it, you know, let's say this was producing, the source was producing 10 radiation. So depending on the thickness, that thickness would impede some. So let's say the right thickness had to be 6. It would cut the radiation being come out by, so the aluminum has to be a particular thickness, right? That's why this is their quality control, right? It can be too thin, can be too thick. So the radiation detector is trying to say, like, hey, it's gonna shoot out 10 radiations, and I'm gonna, as long as, if I see 10, if I count 10, then that means there's no aluminum in front of me, because everything the source is emitting, I'm detecting it. So, but it has to be 6, and if it's not 6, I'll raise an alarm that, hey, you're doing something wrong over here, press these harder. So the aluminum is squeezed a little more. And if this is, if you're not getting anything, then that means the aluminum is too thick. So what is the most suitable radioactive source for this system? So it has to be the beta source, because that is hindered a bit by aluminum, or like small metals with small thicknesses, right? It's sensitive to that. Gamma is so incredibly penetrating that a thin sheet of aluminum won't be able to stop it. So you won't be able to detect the thickness with gamma, right? And another interesting point over here is 1 hours or 6 years. Which one do you go for, right? So you'll have to understand that if the half-life of a source is 1 hour, you'll probably have to, change this every 10 or 15 minutes, the source. Why? Because it's gonna half in quantity and its radioactive emission in 1 hour. So this 10 is going to go down to 6, and you're like, what? This radiation detector is going to get confused. Because it can only detect what it's seeing, right? If this starts by 1 hour later, if this starts emitting 5 radioactive source, even though the aluminum is fine, the roller will go like, the radioactive detector won't detect 6, and it'll start raising alarm. So you'll have to keep on changing the source every 10-15 minutes or something, right? But if it's 6 years, you can last the system can last for at least a year or slightly more than that without you having to do anything. So some usability metric over here. Interesting question. More on the common sense side than anything else. So it has to be beta, and it has to be a longer period than an hour, like at least months, if not years, right? So the correct answer is B. A uniform rod weighs 5 newtons and is held at rest. The diagram shows the forces acting on the rod. Now, the forces that are trying to move it up are 10 newtons, and the forces that are trying to move it down are 5 newtons, 3 newtons, 2 newtons. Cancels out, net effect is 0, it does not move. But if this is hanging by a thread and the weight is through the center, it would stay balanced, but there is uneven weight on both sides. So this will start moving clockwise. It'll start to rotate, but won't move. So the correct answer is D over here, where this rod will start to move and rotate and not move. Interesting. Answer is D. Work is done when a force of 400 Newton pulls a crate of weight 500 Newton at a constant speed along a ramp as shown. So it's being pulled up. Part of the work done is increases the gravitational potential energy, E, of the crate, and the rest of the work done is W against friction. what are the values of E and W? So E is relatively easy to calculate. It's going to be potential energy, right? So it's mgh. Mg is just the weight, which is 500 times 8 rows 3 meters. That's the height it attained, 1500. Okay. What is the work done against friction? That's not the total work done. That's the work done against friction. Okay, you did some work. That work translated into some gain in potential energy and fighting friction. So multiple things is done. So it's trying to ask, what is the work done against friction? So work can be used in many ways. Work is just a, okay, where was this energy? Where did it go? So there were two works done, right? Actually, that's how the question's phrasing it. There were two works done. When you pushed it against this slope like that, that was the total work you did, because that's the 400 in that line, right? So the total work done was actually the work done against the work done to bring the object to this height, which was the potential energy, voila. So it was work done, but all of that turned into potential energy. So that's just equal to E. So I'll just change that in a bit. And the other work done was, they're saying it was only against friction. So the total work you did was either against friction or the potential energy. So this was E, which is 1500, and work done against friction counted to all your efforts, whatever you put in. And whatever you put in was actually 400 newtons in the direction you moved it in, which is 5 meters. The total work you did was actually F into D, which is 400 times 5, E plus. So WF, going off screen, is 2000 rearrange minus 1500. Comes out to bunch. So, and if you think about it, it makes more and more sense, right? If all of the work done, because a lot of people probably did was, they probably took 400, so that's fighting friction, and multiply by that by 5, because friction is, parallel to this plane. So, but if all of that work was friction, then there was nothing changed to, none of your work or effort changed to potential energy. So this object, this block, would not have attained any height if all of that work done was equal to friction, right? So the friction was actually just 500 newtons. Very interesting question, a very A-level concept. That's discussed a lot more freely and frequently in A levels. The answer is A. The resistance R of a wire increases uniformly with the temperature. The value of R at the fixed points are shown in the table. So at 0, it's 100, and yeah, over here it's 250. So it's changing by, when this changes by 100, this changes by actually 150, right? Because from 100 it went to, so let's try drawing a graph for this. If you know your y equals to mx plus c, you'll have a way easier time doing this question. This is your resistance, this is your T, and it starts at 100 and goes all the way up to 250, straight line, right? And this is your 100, and this is your 0. Sorry, this is your 250, and you know this height is actually, this height of the triangle, let's kind of actually make it into a triangle, is actually 150, and the base length is 100. So the gradient is height over the base of this triangle, which is 1.5. So putting all of this in equation form, matching it to y equals to mx plus c, our y-axis is our resistance, that's how I made it. Gradient we found out is 1.5, x is our temperature, plus c is our y-intercept, which is 100, right? And what is the temperature when R is 160? To 1.5 T plus 100, that's T equals to 60 over 1.5, which is, I think I should be able to do this in my head, 40. Comes out to be 40 degrees Celsius. Correct answer is B. An equation of a wave is given to us as velocity is f lambda. Lambda, they're saying, is 0.15 meters and speed is 3.02 times 10 to the power 8. So what is, the wavelength, this is the wavelength, lambda, right? So V equals to lambda equals to f, which is 3 times 10 to the power 8 divided by lambda, which is 0.15. So let's do something easy. What's 3 divided by 0.15? Just 3. I'm getting 20. This should be 20 times 10 to the power 8, or 2.0 times 10 to the power 9. Our correct answer is C. What is one use of ultrasound? Cleaning jewelry, satellite communication, fluorescent tubes, optic fibers. Cleaning jewelry, satellite communication. Okay, satellite communication is kind of out because space doesn't really, sound. There's no particles, it's empty vacuum. Fluorescent and opticals are talking about light. So I think A is the correct answer, right? A step-down transformer has a primary coil and a secondary coil wound on a soft iron core. Step down brings the voltage down. The primary coil is connected to 6 and 6-volt direct current supply. Statement about the transformer is correct. The output voltage is, shouldn't this be AC? The output voltage is equal to less than 6 but more than 0, sure. There's actually, I'm gonna go with transformers work with AC, don't they? An oscilloscope is used to measure potential difference. The trace with no input is connected is shown. Okay, beam is going, there's one division. 1.5 volt DC supply is connected to the oscilloscope, right? The Y gain is set to 0.5 volts. So at 1.5, this point will move over here. It's gonna move over here, and then what's gonna happen? The time base is set. So think of this screen is moving towards the left at 0.5 meter per second, and it's over here. And it's a direct supply, so it's gonna be constant throughout all times, right? So it's gonna be a straight horizontal line. The correct answer is C. Right? Interesting. What increases when a liquid becomes a gas at its boiling point? The average kinetic energy of the molecule, the molecular size, the molecular spacing, the total number of molecules. Okay. Why would molecule number change or their size change? And I'm routing for C. And I'm going to shy away from the average kinetic energy because the temperature is stable when the gas changes its state, right? The temperature is constant, and the temperature is a strong indicator is the indicator for the average kinetic energy. A wire has length 0.5 meter and a cross-sectional area of that much. So let's go with it's L and the cross-sectional area is A and it has a resistance of 0.5. So 0.5 centimeter, 0.5 ohm, sorry, at L and area being A. So another wire of the same material has a length of 2 meters, which is 4 times the. So this is 4 times, so it's turning 4L. So the resistance should increase proportionally. It's 3.0 times 0.75 times 4, right? And the area for this wire, I haven't really changed the area yet. But they're saying the area is also changing. The area is 0.5, which is half. The area is now, the new area is half, and the length is still 4L. Add that, the area will increase the resistance by doubling it, because the area is halved, there's more traffic on the road, the traffic is doubled if the width of the road is halved. So same way, resistivity or resistance is increased if the area is halved. More traffic for those electrons, more hindrance. Correct answer is D. The diagram shows the trace on an oscilloscope screen. The first peak occurs when the pulse sound is emitted. The second smaller peak, the echo is received from the wall. So the initial peak and the initial sound and the echo of it, right? Takes 3 seconds. The trace moves at 24 milliseconds. So this entire length is 24 milliseconds. Divide that by 8, and how long does it for the sound to travel to the wall? So divide that by 8, multiply that by 3, right? That's the time it takes for the echo to be heard after the initial pulse. So I'll half that because that's double the distance, because you know how it works. Wall, speaker, kind of like that. Speaker, boop, boop. Okay, that's horrible. Right, okay, let's go with this. Emits a sound, poop, poop. So it traveled twice. How long does it take for it to just to reach the wall? Half the time, right? So I'm halving it. So 24 divided by 8 is 3. 3 times 3 is 9. Half of 9 is 4.5. A is our answer. A rectangular block of metal has a weight of 6 newtons and measures 3 by 4 by 5. So let's make that block 3 by 4 by 5. That's 4, that's 3, and that's 5. That is the block of Khazad Doom. The block. All right. So they're asking, what is the smallest pressure that can be exerted while resting on a horizontal surface? So the weight, the force is constant, the force is going to be downwards, and it's 6 newtons, right? How do we minimize the pressure? By maximizing the area, right? So what combination of these will have the largest area? How it's exactly lying right now will have the maximum area in contact. So that maximum area, which you can see, right, all that is going to support our cause of minimizing the impact and minimizing the pressure built up because of the force. So that minimum pressure is going to be force per unit area. force is 6 newtons, not a heavy one. Area is 4 centimeter. Thank God it's in centimeter, which is 4 times 5 is 20. 0.3, I'm guessing. Newton per centimeter squared. Correct answer is B. Ultrasound is used to map the ocean floor. During one survey, the depth of water is 1200 meters, and ultrasound pulse is sent from the surface and it returns to the ship. So this is 1200 centimeter meter, right? And yeah, so immediately after the echo comes, in period of 8 seconds, 5 pulses are sent down from the surface. During one survey, so you sent 5, right? So what is the speed of the ultrasound? So we might not get an exact answer. Very interesting question. So you ended up managing to send 5 pulses, because one right after the other you send them. So 8. So for an average pulse is 8 divided by 5. 8 over 5, which is 8 over 5 is, I don't know. 8 over 5 is 1.6. It takes 1.6 seconds for the pulse to go and come back. So it probably took it 0.8 seconds to reach the floor. Sorry, I said meter per second. I meant just seconds. That's just time. Seconds, right? So it took it 8 seconds to reach the ground. So the velocity is the distance traveled per time. That's interesting. Pretty fast. 1500. It traveled 1500 meter per second. Correct answer is D.